Not paying attention today. Okay, so we were talking about a little text processing on Tuesday. We were talking about the how you might handle text, and the specific type of text processing we were doing was called bag of words. So with bag of words, we don't care about the order of the words, we just care about the frequency of the words. So normally what you do is you generate a ordered dictionary. Now it has to be ordered because you are going to build a feature vector off of it. And that ordered dictionary is going to be basically all the words that occur in all of your documents. And ordered probably, it doesn't matter how it's ordered. Often you'll order it by, just frequency so that you can do some glancing at it and see if it makes sense. But that doesn't really matter. Doesn't matter where the positions of the words are because you don't really care. Then each document is represented by a vector of word counts. So you take all of your words in your dictionary. That becomes a new document is going to be the length of that dictionary. And then you just count the words. And anytime you have a word in the document, you make its corresponding position in that feature vector, you increase the count of it. So like in our example here, the x vector is going to be all the words in the dictionary. A bunch of them are going to be 0 because those words didn't occur in this document. And some of them are going to be non-zero. This is probably not a real document. You probably wouldn't have a document with 37 mentions of car, 29 mentions of truck, and no other mentions. That would be a fairly poor document. But the idea is the same. You just count up words, you put them in the right position. So a collection of documents, this is the same data vector we see over and over. You just take your data, your x's, your individual x's from all your documents, you transpose them, and then you pile them up. You concatenate them. It's just your standard X document that we've seen before. Standard X matrix that we've seen before. Then if you want to, the first thing we might want to do is query against that document set. So you'd write a query, and the things that you want to query, if I write a search query and I want to search for car, I would put a count of 1 in the car position. And if I wanted to search for something else, I'd put a count of 1 in that other position. Now, you usually just use counts of 1 because we're going to normalize out the size of the documents. So the size of the query doesn't matter. It'll always get some scaling according to how many words are in the query. So that's kind of the how you build a query. And then to find documents that are matching that query, you just do cosine distance to calculate nearest neighbors. We talked about cosine distance. It's just the dot product between the two vectors, and it's normalized by the size of the vectors. It isn't actually a distance. It's a similarity. It'll be bigger when the things are more alike, and it'll be 0 when there's no overlap. So that's where we left it. We talked briefly about TF-IDF, which is a way to reweight the counts and the word importance. I didn't write it up here. You'll have to go look at the other thing. But it's just the more often a word occurs across your whole corpus, the less of a weight you'll give it, because the more common a word is, the less important it is. So you often just weight things, downweight things that occur a lot, or conversely upweight things that don't occur very often. Okay, so we got this big feature vector, but there's a problem with the feature vector, and it's a problem that really has to do with synonyms in language. So when I write out my dictionary, I'm probably going to have some entries that are, depending on what my topics are. I'll probably have some entries where documents talk about cars by using the word car, and I might have some documents where they talk about cars by using the word auto. So this is really an issue when you're doing a query. If you write a query against car, it won't find the documents that use the synonym, auto. So we have to figure out a way to sort of equalize out this problem where instead of having a document with all car and no auto, you kind of increase the count of auto and you decrease the count of car. Now, why are we able to do that? We're able to do that because there's a lot of correlation with the other words that occur with car. So car, if you talk about cars, you might have a lot of mentions of, I don't know, gasoline, doors, windows, engine, sort of things like that. And if you talk about autos, you'll often still have those correlated words, the words that occur in the same sort of context. So even though you have synonyms that are occurring sort of independently of each other, that correlation with other words allows you to generalize out that relationship. So you can think of this as sort of doing a smoothing on your data. We're going to take our data, and anywhere where we have the synonyms, we're going to try to smooth out, take down the number of references of car, increase the number of references of auto, and make sort of a smoother space where there aren't these sharp references to anything. And we've already done this. We did this with PCA, essentially. We did this, we looked at PCA for smoothing. You guys had an assignment where you did PCA for smoothing. So we're going to use, actually, SVD to do this. So if we take our X, we can form our SVD. That's just the SVD decomposition that we've seen before. We don't even have to normalize anything. We can leave the means. It can be a non-zero mean. It might help to make it a zero mean, but it's not required. But because the SVD will work on non-zero means. Now, you won't get principal components if you take non-zero means, but you'll still get something that's probably sensible. So given this, this is basically your decomposition in a high-dimensional space of, it's in the same space as the size of the dictionary. And then we're going to be able to compress it by only taking a subset of those eigenvectors that come out of this decomposition. So we're going to form a new X, which is going to be the U. And we're going to say S, S, S. And that just means we've chopped off anything beyond the S size components. So just like PCA, how we only took S number of eigenvectors, we're going to do the same thing here, is we're going to just drop a bunch of data. Now, we could look at this data in two ways. We could look at it, when we do the query, we could look at it in this new lower dimensional space, or we can look at it back in the original space. Either way will work. In the lower dimensional space, it'll be more compressed. The queries, you take a query, you project it down to this lower dimensional space, basically the rotated space, and you take your original documents, and you could do the similarity measures in that lower dimensional space. Or you could do it in the high dimensional space, the original space, just by projecting back. This is actually the projection back. You'd have to take just the U epsilon to get the lower level projection. All right, so that's kind of the way we're going to do sort of handle this synonym issue. So I think, actually I'm on the wrong page here, but we have an example of this, if I can find it somewhere. Clustering. Okay, you guys just can take a break while I scroll. Oh, come on. Here it is. Almost there. All right. Haha. Okay, so what we see here, there's two documents, some fixed dictionary, it doesn't matter what we were using. And what we did is we did this smoothing process down to 1,000 dimensions. I don't actually know if it said how big the original was. Yeah, I don't know exactly how big the original was. But we took it down to 1,000 intermediate dimensions. Then we expanded it back out to the original space. So it did this sort of synonym reweighting where the synonyms were sort of smoothed out so you get a little bit on both of them. So what you see here is we're only looking at the first 100 words. Doesn't seem like 100 words, but and you see the frequencies of the different words. And so blue was the original and red is the smoothed. And what you generally are going to see is the big spikes will come down and the low ones will be pushed up a little bit. That's what we normally see. Now you see some of these are kind of odd, like this reference went all the way down to 0. That seems like an odd thing. You normally wouldn't expect it to go all the way to 0, but it can happen. You don't have really control of how it's going to smooth it. You just have the number of dimensions. It's possible it needed more than 1,000 dimensions to smooth this properly. It's possible that word just is only used in one document, and so it doesn't have good correlation with other things. Although it's a frequent word, so that can't be actually. It could be that word has a lot of different meanings for some reason. It's hard to say. So this one is just a different document. Again, you see the originals, some of the big spikes come down really low. Again, I'm not sure why they went down to 0. And it puts some weight into other references. So it's actually possible that basically this is the more common word, and this is a common usage within the context, and this is some odd word. And so the weight on this word came down, and it got pushed into these other ones. It's really hard to figure out how it's doing the transformation of the space. All you can say is that it uses the context to sort of rearrange compress the space in some way. So it uses the words that occur along with any individual word to sort of compress that space. So there's one more example I wanted to do, or I wanted to look at, not that one. I'm having a good time finding things today. This is actually an example of MDS. You can do MDS on your documents just like you could do anything, or on any data set. I don't actually think they did the SVD on this one. They just took the data set directly. And what you saw, what MDS tries to do is it tries to lay out this high-dimensional space in a low-dimensional, two-dimensional space, which is going to, there's going to be a lot of loss. But you see all the documents sort of in their space, and then what we did is we did like quantiles or third tiles, I guess, whatever a split into 3 is. And we split it into 3 groups along each dimension. Now, the dimensions have no meaning here, but we can look at the kind of words that were common in each of those quantiles. So if we look at this upper left sort of thing, we see these are all NIPS documents, so they're all some sort of computer machine learning-ish kind of things. So up in the left upper hand thing, you see kind of, they're talking about modeling, doing some sort of image models, something like that. If you come down to this lower quadrant, they're talking more theoretical things, algorithms. If you come over here, you have a little quadrant that has basically stuff related to neural nets. So it's all neural net stuff. And so you can see this is all based on bag of words. It didn't have anything but bag of words, but when you take the MDS of it, you actually can break it up pretty nicely. Now, you mostly just do MDS to view your, kind of as an example of how you might view your documents, but generally wouldn't use MDS for any kind of real analysis. Top left and middle left. It can happen because the words that are here are the most common words for the documents in that quadrant. So there's nothing that says that visual will only occur in documents in a specific place. There's nothing that forces that. So it can happen. There's nothing that controls for that. Now, you wouldn't expect that to happen a lot, but it certainly, there could be, if you didn't remove stop words, like the would occur everywhere, and you'd find that all over the place. So that's a good example of something that is super common. Now, if you did TF-IDF, it would eliminate some of that because it would downweight common words, so you'd only get the less common ones. But to answer your question, that's not unusual. There's nothing that guarantees it either way. All right, so let's see what else I had here. This is called latent semantic analysis, for what it's worth, that SVD process. It's right up there. That's just the term we use for doing, looking at that latent space, that hidden space that we talk about that's lower dimensional. So you can also do some analysis. You can actually use that space to do some additional things that we're not going to talk about. But generally, you just use it for a smoothing technique.
So if you were trying to build a classifier for words, from what I understood from previous sections about PCA and things like that, PCA can't necessarily improve your accuracy. It can just reduce the amount of data that you have. So are you
It can certainly improve the accuracy. Remember, it's doing a smoothing task in some ways. So if your data has a lot of noise in it, PCA will smooth out that noise. And so you can actually improve your classification it depends on a lot of factors, but there's nothing to say that you might not improve your classification. You're making the task, so if you have a real high dimensional space, one of two things will have to happen. You'll either have to, well, you don't have to do this, but either the classification algorithm is going to have to compress that space into some good representation, or PCA can do some of the work to compress that space. PCA might do a more intelligent job at it, whereas the classifier might just be creating, a linear cut, and it might just tilt it, so that linear cut makes sense. Now, it could do just as well. It can work in that high dimensional space, the classifier. So it's really an open question. If you think with words, it probably would help to work in that lower dimensional space. For a lot of things, I don't know if it would. Generally, people don't project down into a lower dimensional space, except for something called embeddings that we'll probably talk about later, which are actually a low dimensional projection of things. And then actually you do use, with neural nets especially, use basically a really low dimensional space. Maybe you'd use a 64 dimensions for an image, which is a huge amount of compression on an image. So you do actually do this sometimes, but fairly rare in just a straight linear classifier. Okay, so now we want to talk about something called topic models. This is another way to handle, to process documents. A topic model, as we talked about, word counts can kind of expose similarity among documents. Documents with similar word counts will be kind of similar. So we might want to sort of cluster documents that were generated from the same, what they're going to call topics. So a topic is basically just a cluster of documents. So if we looked at this example, oh, I didn't switch my thing, and you guys didn't call me on it. If we look at this example, we could probably find a topic for each of these quadrants that might make sense, where all of the papers that happened in that individual quadrant came from that same topic. So we'd have 9 topics. They'd each have some papers in them, and they'd correspond to these 9 quantiles. Now, the algorithm we're going to talk about probably wouldn't come up with this particular MDS layout of it, so that's just kind of an example. But conceptually, it's the same thing. You're going to have 9 quadrants or 9 topics, and the documents are all going to fall into that. Let's go back to this guy. So it's called topic models, and basically this looks just like clustering did when we did clustering via EM. You're going to have a set of topics, and there's going to be k of them, and you have to choose k a priori. You can try different k's, but there's nothing that's going to guide you to a certain number of k's, or a certain number of topics, rather. And then given a document, if you knew the topics, we'll know basically the words that are the probability of words occurring in that document. So what we're going to do is, given a document, if you wanted to generate a document and you knew the topic, we're going to take IID samples of words from that topic's probability distribution. So each topic is going to have a multinomial distribution over words. So the one topic will have the probability weight towards one set of words. Another topic will have it towards a different set of words. And this is a lot like the means of a cluster, but instead they're going to be the words that are going to happen in a document. So when you want to generate a document, if we look at a generative model, you'd first choose the topic, and then given the topic, you would sample a number of words. Now you can get multiple counts of any given word because you're just sampling IID, so a word can occur multiple times, and we're going to be able to figure out how the words and the topics are set up, just like we could do with clustering. So again, the word order doesn't matter, just because we're just sampling words. So given a set of documents, basically your X, we want to find 2 things. We want to find the word given topic probabilities, which is generally written as P. P will be a vector, and it'll be there'll be 1 for every topic. And that P will be a vector of probabilities over each of the words. So if your dictionary is 100 words, P will be a 100-dimensional vector, and it'll sum to 1 and just be the probability of each time you sample a word that word would come up. And then the other thing we want to find is basically what we called the mixing probability before, but it's the number of documents, basically the chance that a particular document belongs to any given topic. So if you have a corpus that has 2 topics and 30% of the documents belong to one topic and 70% belong to the other, your mixing probabilities would be 0.3 and 0.7, just like the clusters. So sometimes you have more documents in a given cluster, and we have to take that into account. Once we have that, we can write a probability. Again, we're going to use we're going to represent this. This theta is going to be all of the parameters. You'll have these p-values, one for each cluster, and they're vectors of the probabilities. Anytime I say cluster here, you can substitute topic. They're effectively the same. For historical reasons, they're called topics. Most of the research calls it topics, but they're just clusters of documents. So you have these are scalars. These are vectors. And of course, now what we want to do is we want to learn them. So we have to have some probability definition. The probability of a vector, a document vector, given theta, we can write out. And this is over all of the, that's over the topics. So it's the probability of the document given the topic. And then that's times the probability, this is given the topic and theta. And then the probability of the topic given theta. Now this should look a lot like the clustering we did before with the GMM. The only difference, or the big difference, is instead of having a mean, we have this, the probability is over all of the words. So it's a little bit of a different thing you have to learn. Now, we can learn this just like we can learn with the EM, we can learn the clustering. We use EM here in the exact same way. We introduce a delta, and that delta is going to be the assignment, an assignment of a document to a topic. Those are a hidden variable. We don't know them, but we can write out the probability to, if we knew that those assignments, we can figure out the parameters, and so we can write out this probability that has the hidden variables in it, and then we can use EM to take the expectation over all those assignments, and we can get rid of it, and we come out with another nice closed form solution. So much like EM for the clustering, we're going to come up with a weight that is a weight that basically assigns a document to a topic. The form of this is somewhat different just because of the way the probability works out. I don't know why I always put my notes on the wrong side. So this is going to be a product over all of the words of the probability of the jth topic and the kth word. And since a word can occur multiple times in a document, we have to take the document vector and the number of times that word occurs. We have to take the probability of that exponent. And let's see, that's there. And then we have to add in the mixing probability. This is over basically the normalizing factor, which is going to be, this is the product, not the mixing probability. The product over all the words of the probability of a given word, of a topic and that word, to the exponent of the document and the number of times the word occurs, times the probability of that guy. This summation is actually over all of this. So that's the W, the weighting vector that we got, just like in clustering. Conceptually, it's the same. It's much different because we're coming up with probabilities instead of means, but that's what it looks like. And then, because we're using EM, we're going to be doing an iterative approach where we have some initial theta at time n, and we're going to come up with a new theta at time n plus 1. So a new theta means that we're going to have a new p for each of the clusters. And this is a fairly simple one. We go over all the documents, and we take the weight for that given cluster, and that is over basically a normalizing factor of all the things times the vector of all ones. Basically, this is just sums up all the counts in the word times wij. So it's just a normalizing factor that adjusts for the number of words in a given document and uses the weights. Similarly, for the mixing probabilities, we're going to get a pretty easy thing where we just take the weights over all the documents over the number of documents. And that's it. That's topic modeling. So pretty simple, pretty straightforward, very much like doing EM for clustering.
I'm not sure why we raise the product with the K. Why do we raise
Okay, so if a document, if let's say you have let's say you have two words, word 1 and word 2. And this guy has a 0.3. The P for a given topic is 0.3 and 0.7. Has to add up to 1 because it's a multinomial distribution. This is a vector, and let's say this is for topic J. Now we have a document. This is going to be an equal to a vector. So let's call this x1. And let's say there's 3 mentions of this and 1 mention of this. So what's the probability that we sampled that? Well, we are doing independent samples, so we're drawing from that multinomial 4 times because it's of length 4. So the probability is going to be 0.3 to the third, because we have a count of 3, times 0.7 to the 1. So that's why we have the exponents, because the counts are not just 1 or 0, they're actually a count of the number of times that occurred. Now there's a normalizing factor here. There's some C that is a very complicated formula that actually drops out. It's a big factorial calculation because you have to adjust for the number of words to get all the probabilities correct. But when you do the EM, those adjustments for the length all cancel out. So that's why I didn't show it.
And so K is a subscript. When we record it?
Yeah. Yeah, so this would be, in that formula, K probably was a bad choice because uppercase is the number of topics, but lowercase was the number of words. So this would be K equal 1, K equal 2, sort of thing when you walk over all of the different word indices. So yeah, so this means document I, the kth word. Yeah, this is, if you look at the book, he doesn't even put the parentheses in, so he writes them like this. JK. He writes that sort of thing. And so it's even more confusing when you look at that because you're like, is it P, some specific P, or is it the power, or, you know, a sort of thing. So that's why I specifically made it explicit that there's a power there. And again, it's just the number of times that word, because you're doing IID samples. You could look up a multinomial, multiple samples from a multinomial, and it'd give you that formula. Any other questions? That's a vector of all ones. Basically, when you take a dot product between a vector and a vector of all ones, you're just summing up all of the values in that. So it's basically the sum of the counts, because you have to normalize by the size of the document, which is the sum of the counts, and you have to normalize by the weight. So you got to normalize by both of them. So that's just ends up being the counts. Sometimes we're going to actually see that today when we're talking about regression, possibly, if we get that far. This is a real common thing to basically say the sum of everything. You can write things like the mean of something by writing, say, x over n. That comes up by taking all the x's, take it times 1, so you add them all up, and then you divide by some n to get the mean. It's just a nice way to do the sum of things sometimes. Anything else? That's what I was just talking about. This is a vector of, and so when you have x, xi is going to be some vector. Well, we transpose it, so it's going to be multiple things. So it'll be a, b, c, d. And then this becomes a plus b plus c plus d. It's just an easy way to sum things. Little trick of linear algebra. What's up?
So it's a very top one. So EJK is the probability of a word for a topic.
Yes.
And the alpha under the probability of a topic.
It's actually the same thing. I don't know why I put a comma in one of them and not a comma in the other. This comma probably shouldn't be there. It's the same. You're going to have a vector of, for each topic, you're going to have a vector p. And that p is the probabilities of the words occurring in that topic. And so this is saying the jth topic, the kth word. This is saying we got to do a normalization. Basically, we're doing a marginalization here. So we're going to walk over all of the topics, and we're going to take the lth topic, kth word. So you're going to take the p vector that applies to topic L, and you're going to look at the kth value of it. Cool? Oh, another one? This is the most questions I've ever had.
Top part of the weight. So on the top part, when you were mentioning the big K and small K.
Yep.
So the PJK is a small K.
Yeah, these are all small k's. This is the k over. This is just because we did IJK, and it's not the number of topics. This is the number of words. So it's a product over the number of words. No, it's all small k. This will be the document I, word number k. Again, this is inside of this product, and so k is going to be an index from 1 to the number of words, and you have to take the exponent on each one of those. There's a lot of exponents moving around here, or a lot of indices rather. Okay, anything else? All right, that must have been the most complicated formula we've ever had. Okay, cool. That is topic modeling. I don't think we have an example of topic modeling. Yeah, I don't think there's a good example. I was going to make one up. Maybe I'll make one up for the next class, just to show you how topic modeling can actually do a pretty good job of recreating things. So I'll think about that. Now let's go. I'm going to find the pictures so I know where I am. Okay. assignment, I believe it's 7 or 8, or 8 or 9, I can't remember. We decided to sort of combine those, and they're going to be 2 separate assignments, but they're going to be on the same, basically, both of them will be text processing or text handling using Bag of Words. We'll probably have you do the SVD on it, some sort of topic modeling on it, and possibly some sort of categorization using some regression or stuff we're going to talk about in the next couple days. So this stuff's actually things we're going to do. We just haven't decided quite what it's going to be. Hopefully it'll be more interesting than the assignments we had planned, which were pretty boring. One of them was pretty light on any kind of thing that you guys could have learned, which was a little frustrating. Okay, so the next thing we're going to start in, and this is a new chapter, new topic, and this is called regression. Regression is just predicting values from some input X. So with classification, we were predicting labels. So we were predicting discrete things, A, B, C. You know, X vector is predicted to be A, B, or C. In this case, we're going to predict a real value. So we're going to take some input X, this will be a vector, and we're going to predict what is usually called Y. This is a really common activity in machine learning. The 3 most common things you're going to do in machine learning are going to be regression, classification, and then probably clustering. Those are the 3 big ones. Now the techniques you use a lot of what we're going to talk about for the next couple days are going to be techniques that you use to do regression, but this is really common, these are the really common sort of things you do with machine learning. Then there's a bunch of other ones we'll talk about in a week or so or 2 weeks that are less common, still interesting, but aren't used nearly as much as classification, regression. I've certainly never used them in any work I've done. I've always done clustering, classification, and regression. So examples of regression, there's a lot of them. You can think of anything you had to predict a value. So one of the ones that David always liked to use is there's a site called Zillow, which basically will give you the value of a house given some parameters. So they basically took a bunch of data from the housing market, where they looked at size of the house, number of rooms, square footage, location, I don't know what color it was painted, all sorts of different things. And then they try to predict the cost of that house, how much you'd have to pay for that house. Now, these are wildly inaccurate. This is a really hard task, and regressions often are very difficult to do, but you could definitely do that sort of thing and get maybe a good estimate of that house value. There's a lot more examples. At YouTube, we'd predict the view time of a video. So if someone was to click on a video, we'd predict the view time. And that's a regression problem. And we do that so that we could guess sort of, if we showed you this video on the home page, we could estimate sort of the chance that you'll click on it, and then given that you click on it, how long you'll view it. And that'll give you sort of the probabilistic interpretation of how much that video is worth. Anything where you're estimating the cost of something, just like Zillow, is a regression problem. So anything in like the stock market is going to be regression. Any kind of baking or actuary stuff is going to be regression. For that matter, almost all ranking is done using some regression. So any kind of search engine or ranking on a website for Facebook, videos, anything, there's probably regression under the hood to some extent. So regression is really, really common. You see machine learning that uses regression is all over the place. Now, one of the things let's look at this. Let's look at this example so you guys can see what regression actually looks like. Okay, so here's a regression of, there's actually two different examples here. The left one here is somebody came along and measured the length of fish versus their weight. So they caught a bunch of fish, they measured the length and the weight, and then they tried to fit a line that, given the length, they predict the weight. And what you see here is, okay, first of all, obviously there's a problem with this. We're trying to use a line to predict what is obviously a curve. We're going to deal with that we might not get to it today, but we can deal with that. The other thing you are going to get is you'll notice that some of these length measurements will have multiple things, weight measurements. And so even for a given input x, you'll often have multiple y's. So there's some sort of noise process going on here. Either there's noise in the measurements, there's noise in the real world, there's something happening here. And so regression is going to have to deal with that somehow. It's going to have to deal with the fact that when you make a function for regression, it's only going to be able to predict one value. You put in x, it's going to spit out y. So like here, if you put in, I don't know, 43, it's going to spit out a little bit more than 800. Even though there's this really fat fish up here, and there's this slightly anemic fish right there, it's just got to make a guess. It can't do a perfect job. Literally, there's nothing that regression can do to get these values because there's multiple values for the same input. You'll also notice that regression can make terrible mistakes. So if you look at a fish that is only 10 centimeters in length, the weight, according to this, should be about negative 100. So obviously, there's a problem with that regression that it's making a prediction that doesn't even make sense. It can't deal with that curve, and so it's, at the edges, it's doing some sort of weird thing. That often will happen in sort of a situation where you have a curve, but it'll also happen when you try to do a prediction outside of where your data was sampled from. So once you get outside of the domain that you originally sampled from, the regression's allowed to do whatever it wants. It can go off the rails completely because it had no data constraining it. So often, if you try to do a sample from outside of the distribution you trained on, bad things will happen. All right, so let's look at this a little more formally. We're going to have some input x. I'll switch this back for you guys. Heard a lot of grumbling there. And we're going to have an output y. This is a supervised learning. Unlike clustering, we have labels. Those labels are real values. So this is a single scalar. And it's a real value of some sort. And then this is, of course, our standard feature vector. We're going to make a prediction, y, which is going to be some function of the input vector x. And then to deal with the fact that we know that there will be, A, will make mistakes, and B, there might actually be multiple data points for the same input that have a different output, we have to add some sort of conceptual noise. I don't know how to make that one very well. I can't even remember what that. Anybody know what this Greek letter is? Is it psi? It probably is. That looks like psi to me. Kind of an S-like. Yeah, I've never been able to draw that correctly. So it's a noise. We treat it as noise. We don't care about the form, except that it's zero mean. And we can guarantee that it's zero mean because if it wasn't zero mean, we could just push whatever non-zero mean we could push into the function prediction. So we can arbitrarily move the mean around over into the function just by adding add some value to the function prediction. We want to figure out this function, basically, from the data. That's really going to be the task of regression, is figuring out f. We don't really ever figure out sigma there. That's noise. We'll never be able to predict it. It's just noise. You can do some work to kind of get a feel for how much noise it is, and we're going to look at that, but you can't predict for any given prediction how much noise there really is. That's not even true. For any given prediction, you can actually get an idea of how much noise there could be there, how much variance for that prediction there is. Now, we're not going to do that. Not many regression techniques actually do that, but that's definitely possible. But it'll never, just like anything, we're basically predicting the mean of something, and we'll never really know how much that mean is off. Okay, the one thing you should be aware of is that this relationship is only correlation, not causation. A classic example of this is if you took a data set where you had the age of children and their reading ability, you would get you could fit a regression against that, and what you'd see is that as the age increased, the reading ability increased. But you wouldn't see. Let me go even farther. I think the example that David gives is they actually, if you measured the foot size of a child versus their reading ability, you could easily draw a regression on that where a small foot doesn't know how to read and a large foot knows how to read. But of course, that's not a causal relationship. It's not like children with small feet are not intelligent. It's that children with small feet are young and haven't learned to read yet. So you got to be careful with regressions. They don't imply causation in any way. Causation is actually a really tricky thing to prove. You have to spend a lot of work, and it's mostly work that comes when you're taking your samples to prove causation. Basically, you have to have some proof that something occurs before another thing, and even then, it might just be some sort of weird correlation. It's really hard to prove causation. The other thing is that regression doesn't always work. So let's look at a couple examples where regression didn't work. We're going to jump back and forth to the examples a lot today. So here's two examples where the regression is fairly poor. On the left-hand side, this is the thorax length of, I think, a fruit fly. Yeah, female fruit flies, and their lifespan. And so you can see that there's a lot of variance in the data. And because of that, there's definitely a trend there. As fruit flies get longer, their lifespan is longer. And so we could definitely do some regression, get a trend, but we can't do a very good job on it. We also, again, can't assign causation here because we don't know that why a higher length would result in a longer lifespan. It might just be that they die sooner when they're you die sooner. You didn't get a chance to grow as much. Something weird like that. That's not even weird. That would make sense. But I would guess they only measured live fruit flies. The second one is a prediction of temperature versus heart rate in humans. And so you see that this is actually really hard to model. Basically, there's very little correlation between the temperature of your internal temperature and your heart rate. There's probably something there, but this data set, in the way that they looked at it, it's just sort of a cloud. And you're not really doing a very good regression. There's going to be a ton of error in this particular data set. And we're going to look in a second how to measure that error, if we get to that today. Okay, so the things that we're going to need to do with regression, we're going to want to look at how to learn it. That's the first thing. We're going to want to look, is it working? And if it isn't working, what can we do to fix it? And those are the two big things that we're going to look at in regression. And then we're going to look at a bunch of techniques that we use. There's other uses for regression that you'll sometimes see. Let me bounce back to this and look at one more thing. Sometimes you use the regression to do analysis. This particular graph shows 3 batches of, there's a medical device. That medical device releases some amount, or causes some amount of hormone in people. And the question was, is there a difference between the batches of devices? You know, are the devices all working the same, or are they working different? And so if you looked on this graph on the left-hand side, it's kind of hard to say, you know, that A is working better than B, or B is working better than C. And so one thing you can do is you can use regression to basically eliminate forms of variance. So here we did a regression against sort of the time in service and the amount of hormone that's released. We take away that factor by looking at just the residuals, which is what's left over when you remove that regression value. And now what you see is that it's much clearer that there's something weird going on with batch A versus batch C. Batch A, they seem to last longer, but we probably don't care about that. But they all released less hormone, or caused less hormone. I'm not sure what these devices did. Versus batch C. So by using the regression, we can actually get rid of some noise in the system, and we can do some analysis like that. Now, we're not going to look at this. It's just another, a whole other topic of ways you can use regression. We won't examine that kind of analysis, but it is something that is out there. All right, 15 minutes. Spent about 10 minutes switching back and forth. Okay, so we're going to look at linear regression as our first form of regression. Linear regression, just like it sounds, is going to be a linear function on x to generate y. Now that is fairly limiting. But what we're going to find is that linear regression actually works really well. There was a paper from Google years ago now that actually talked about how linear regression was all you need. If you had enough data, linear regression could do basically as good of a job as pretty much any regression technique. Now, unfortunately, that derailed the industry for about 10 years. And now Google will say that neural nets can do anything and linear regression you shouldn't touch. But that's not completely true. But it's certainly, that paper drove people to use linear regression a lot more and not to look at other things. So linear regression, again, it's y is just going to be a linear combination of the input times some beta, which are the parameters. And then there's the squiggly noise. And that is going to be zero mean, as we talked about before. Now, there's one issue with this. If we write it like this, there is no y-intercept. So any regression we did with that formula would have to cross through the origin. So that's going to be a limiting factor. The way we're going to solve that is that we're always going to assume that x, the x that we really use is going to be sort of the original x. So I'll put a little hat on this. And then a 1. And I won't write x hat through all the equations later on, but we include this 1, and that basically gives us an intercept so that we can move the intercept to wherever we want. If you don't do that, you have this very limited regression that always has to go through the origin. Just so it's clear, that will give us a formula that basically, if we talk about the original x times some beta, and we'll get sort of this situation where we have beta 1, beta 2, where this is a scalar, this is the vector, this is the original x. So that's just breaks out that intercept nicely. No, psi is a noise function. That is something we do not predict. This is something, if we looked at that formula earlier, this is going to be our function f of x. This is just noise. Noise or variance, irreducible variance it's often called. Things that we cannot predict, like the fact that you have the same output value or different output values for the same input value. There's nothing we can do about that, so we throw that into the noise function. No, we don't. We're never going to do anything with that. We might be able to predict its variance, how much noise there is, but we don't even know the form of the noise. Now, we're going to make an assumption of the form of the noise to do some of the math here, but we don't really know that the noise follows some pattern, other than its zero mean and its IID. So the noise isn't correlated between different examples. Not 100% accurate or can't be 100% accurate. Remember, if you have different output values for the same input, you can't predict multiple outputs for that same input. These are deterministic functions. They will generate, you put in x, they will generate y that is a single value. So it's not taking some sort of sample. In a second, we're going to treat them like a random variable, but for right now, these f gets a single value out for any input. And so that noise has to deal with that. And so some of that noise is just going to be mistakes we make, meaning that we couldn't fit all the data. And some of that noise is going to be irreducible noise. There's just something about the world where a fish of length 3 will be a weight between 5 and 10. The world is just something, we can't get rid of that. We can never predict that. We can find some mean of it maybe, but we can't do anything about that. So the noise really is just a mathematical formulation. Generally, once you start doing a lot of regression, you kind of stop thinking about that noise. It's just used to do the actual math to figure out how to do the minimization that we want to do. Anything else? You guys are really chatty today. That's good. I'm not complaining. It's just some days I wonder if you're out there. Okay, so having said that we can't predict what that noise is, we're immediately going to make some assumptions about that noise. So we're going to take our linear function, which will be our x times our beta plus our squiggly noise. And we're going to assume this is a normal with some zero mean and some sigma variance. And we're just going to make that assumption. And that's going to help us find a way to figure out a good regression on this, a good linear regression. So there's two things we can take away from this. One is that if this is a normal, then we can move this xb to the other side, and we know that this expression is a random variable that follows a normal was 0 sigma. Usually it's sigma squared, we write. So that particular expression follows a normal distribution. Using the same logic, we can say that y follows a normal with mean xb and sigma squared. You can look at it either way. Either you could say the normal has a mean of xb, or you could say that y minus xb follows a normal with 0. We're just moving the means around there. That's standard things you can do with probability. Now, if you have a normal, any kind of distribution, the parameters, these are the parameters that we're going to have to predict. And we're going to call this beta hat typically to mean that we're predicting it. It's something that we predicted from the data. So if given a different set of data, we'd probably get a different beta hat prediction. It'd probably be close, but it could certainly be different because every data set's going to get a slightly different line. So we'll always denote this with a hat when we mean that it's a prediction. So given a distribution, what we're going to want to find is the maximum likelihood estimate. This is the way, anytime you have parameters of a distribution, you want to find the maximum likelihood. The way we're going to do that is we're going to take the log likelihood, which is parameterized by beta, and that's going to be equal to 1 over n over the data of the squared loss I missed a step. I'll write in a step here. Here, let me do this. Everybody back up. Can't always be perfect. That's the loss we're going to minimize. So it's the log, basically it's the log of the average of the log probability of the data. And I'm not sure why he wrote data. Did that at one point. It's just the x's, given the betas. And now I'll write out that expression I was about to write out. So this is 1 over n times 1 over 2 sigma times the summation of I times the square of the difference between the label, the yi, and our prediction, squared, plus some stuff that depends on sigma. We don't know what sigma is, so we don't care about what this stuff is. We could figure it out in terms of sigma. It's not going to matter. We're never going to know sigma. Sigma is some unknown parameter, and we're just going to, because we're about to take the maximum of this, we're going to be able to ignore sigma. So the way you take the maximum of this is no, because this expression, this part and this part and this part all come from the definition of a normal. They're just the probability of a normal distribution. That we then take the log. We take the log of that normal distribution. Remember, a normal distribution is 1 over 2 sigma exponential of minus 1/2 over the square. So you end up taking that log over sigma squared. you end up taking that log, the exponential goes away, and stuff gets rearranged, and you come up with this formulation. So that we already just pushed through the log. That's a squiggly garbage. It's not a real technical symbol. It just means that there's some constant. It's a constant that is parameterized by sigma that I just didn't want to write. I could do the math to figure it out, but it's just some other constant that falls out of this equation when we take that log probability. Because there's when you take the log of a division, you get an addition or a subtraction as it is, and so you get some crap at the end. We don't care what it is because what we're about to do, and I'm not going to have time now, but what we're about to do is maximize this, which means that anytime we want to maximize it, the first technique we try is to take the derivative, set it equal to 0, and see what we get. When you have a constant like that, we're going to take the derivative with respect to beta, not with respect to sigma. So because we're not going to take it with respect to sigma, that constant with sigma is just going to fall out, and we don't care. Same thing with these constants up front. When we take the derivatives, they'll still be pulled through into the derivative, but then when we set it equal to 0, we can just multiply by whatever or divide by whatever, and it goes away. So we'll end up with a nice, concise thing that doesn't have any sigmas in it, and is just basically the differential of that guy right in there. All right, ran out of time. Anything else before we go? Okay, cool. I will see you guys next Tuesday. We are here next Tuesday, right? That's not spring break. Spring break's a week after that? Okay. Okay, we got a little time. I'd hate to come in on a spring break.